Okay, let us start. It is a great honor to me to introduce Ronit Rubinfeld. 5 years ago, I was with a short visit to MIT with Andrei Raigorodsky and some other people. And by occasion, I attended a lecture in Microsoft Research, New England. So just 15 minutes before the lecture, someone told me that it would be a nice lecture. I attended it, and it was a brilliant, exciting lecture. And this was presented by Ronit Rubinfeld. So I hope that this lecture will be even more exciting, interesting for all of you. So the topic is local computation and non-exhaustive survey. So thank you very much. Thanks. Ronit, please.
Thank you. So I have news for you. It's the same lecture. No, there's been updates since then. Okay, but it starts the same. So in the last many years, we've all been trying to understand what do you do with really big data. So the context is what happens when you're working with data that is so large that you can't even look at all of the data. Okay, so you can't even hope to even view streaming. You can't store it, and you can't even process in any way all of the data. Okay, so you'd like to deal with extremely large inputs, and there has been a lot of work on what to do when you can't even view all of the data, and it's often talked of as sublinear time algorithms. But today I want to focus on an aspect of sublinear time algorithms where not only can you not view all the input, you also could not hope to process all of the output. Okay, so often when you're running a computation, there's an extremely large input, there's an extremely large output, and just writing the output takes an incredible amount of time. Today we want to talk about what happens when you just want a small portion of the output. I want the ith bit of the output, or I want to know if the edge UV is in the output or not, is there in the graph or not. So I want something very specific. Maybe later I'll use it to do binary search, but I just want a very small portion of the output. And the question is, do I have to compute the whole output in order just to figure out my one portion? Okay, so in order to see all the output, do I need to, first of all, compute all the output? And even if I don't need to compute all the output, do I need to see all the input in order to calculate just this one portion? Now, obviously, there are many functions for which the answer is yes, I have to look at all of the input. But there's a surprising number of things you can do for which the answer is no. And that's what I want to talk about today. Okay, so here's some examples. So these are examples of things that you may already have heard of, but these are examples of places where people have figured out how to calculate a portion of the output without scanning all the input. One area that's received a lot of attention is locally decodable codes. And these are codes where here we think of the input as the encoding of a large message. Okay, so somebody has a message, they encoded it. We have a huge encoding. Now what our output should be is the decoding. It's a decoding algorithm, right? So it should output the decoding of the original large message. Now the question is, maybe I just want to know the ith bit of the original large message. Maybe I don't need the whole message. Do I actually need to decode the whole thing? Or can I just figure out what the ith bit is much faster? Maybe I can. So it turns out that you can design different codes that have this locally decodable property, but are almost as good as the original code. So for most codes that people like to use, you can pretty much achieve the same rates and errors that with locally decodable code. So there's been a lot of work in this area, but this is an example of the type of question we're going to be talking about today. Okay. Similarly, very similarly is a local decompression algorithms. Here the input is compressed data, and the output is, I just want to see the ith bit of the original data before it was compressed. Do I now have to decompress the whole data? Okay, and it turns out that there are compression schemes that work well compared to other known compression schemes and require very few answers to query. So there have been a lot of works on this type of question as well. Yet another scenario where people have looked at how not to have to compute the whole answer is in dealing with large graphs. For example, community detection. You may want to find a good cut near a node V, so you may want to find like a piece. So we may have a notion of a community. These are nodes which I'm more connected to. And then I'd like to find a place where I can cut very few edges and say that's my community. Okay, so like these are people I'm very well connected to, and then I'll cut off a few edges and separate this community from the rest of the graph and say this is one community. Okay, so usually it's defined by the ratio of the number of edges you cut off divided by the number of nodes that you took out. So there's some notions of communities. There are different notions. I'll even talk about one later on when I talk about expansion. But this is something people like to look at. And to find a good community of a specific node is something that many people have considered without going to the whole graph, but just a runtime that depends on the size of your community. So instead of having to go to the whole graph, process the whole graph, find the best possible community for node V, we'll just find something close by, and my running time will be in terms of the best community near me. Okay, other works have looked at PageRank, finding high-degree nodes, and influential dominating sets. So these are a number of questions where people have looked at them in terms of just some other function of the running time is not in terms of the number of nodes, it's sublinear in the number of nodes, it's in terms of something such as the size of the community or the size of an influential set. Okay, and yet I just want to mention one more example of a place where such local algorithms is useful, and that's in online property reconstruction. Perhaps you're given some input. It's supposed to have some special property, like maybe it's supposed to be in sorted order or in some kind of monotone order. But the input was slightly corrupted. Now, I don't know how to get back the original input. Okay, but maybe what at least I can do is get back an input that's close to what I started with that does have the good property. Okay, so I can't fix the noise in the absolute sense. I can't get back the actual values, but I can get back an input that does satisfy this good property. And I'd like to do this in a way that's local, that doesn't require me looking at the whole list, finding the closest input that's sorted, and then figuring out what my value should be. Okay, so I want to correct the input so it's close to the original input. I'm going to assume that it's only slightly corrupted so that this is something hopefully I can do. It has this useful property, whatever it may be, and we'll discuss some examples soon. But for now, let's think of monotonicity. And I'd like that the values are quickly accessible. So here's an example. So here, this is supposed to be in monotone order. Okay, so here we have so I've plotted it as a picture, but you could think of it as being the values 2, 3, 4, 2, 3, 4, and maybe 2, 3, 4, 1, 2, 3, and then 5, 6, 7, something like that, okay? So that's your list. It's not in sorted order because these guys down here are all less than him. So you either need to move these 3 or you need to move these 3. But notice that the guy in the middle, if you just look at his neighbors, he looks fine. If you just look at his neighbors. So you have to do something more interesting than just look at your neighbors. Right? Here you can see this guy needs to be moved up. Or this guy needs to be moved down. Actually, I don't know which. But I can't just look at my neighbors and figure out where I need to go. That's the point. So the point is I need to look at something a little bit more interesting. And it turns out that actually, so here's an example of what you could have moved it to. And so it turns out that you need to look at different neighborhoods, different sized neighborhoods. And there's a logarithmic time way of correcting this. It's not necessarily trivial, so I'm not going to cover it right now. But I just want to say that it actually requires logarithmic time, and it can be done in logarithmic time. And it's very nice, but not completely trivial at all. Okay, so this was in a this was a model suggested by Elon, Chazelle, and Seshadri, but it's been applied in many scenarios. We mentioned monotonicity, but also Lipschitz functions. Those are functions that don't change too much, and that's actually been quite useful in making data private. So in privacy-preserving systems, Raskolnikova and Zha have shown that this Lipschitz correcting ability is very helpful. It's been applied to convexity. It's been applied on graphs, taking a graph and slightly modifying it so that it has a certain property, such as being an expander graph or being connected, being k-connected, having small diameter. And it's even been applied to distributions, some local way of correcting a distribution that might have a little bit of noise so that it has the desired property. Maybe for example, let's take monotonicity. Maybe the distribution is supposed to, maybe the distribution on a single variable, single numbers between 0 and 1 is supposed to be let's say, so it's a finite domain. Let's say it's a distribution on 1 through n, okay? And a p sub I should be at least as big as p sub I minus 1. So it should be monotone increasing. And maybe somebody corrupted the distribution and made it so that it's not monotone increasing. How do I fix it without learning the whole distribution? So that's the type of question that could come up. I could ask the same question on, it's supposed to be a Gaussian, but I want to fix it without learning the parameters of the Gaussian. And there are many other questions you can ask. Okay, so lots of people have looked at such questions, and it seems time for, we'd like a good unifying model because we'd like to understand what are the difficulties with constructing such algorithms. Okay, so let me propose one. Here we have an input. The input is written down. That's somewhere, and I'm going to assume, and this may be a crazy assumption for some people, but I'm going to assume for today's talk that we have random access to this input. Okay, so I can say, what is the value at location I? And I can get it in one step. Okay, so this is not a stream. It's not this is just out there. I can reach it. But I don't necessarily have time to look at the whole input. Now the output is what I want to compute, and I definitely don't have time to write it all down. So I don't have time to compute it, and I don't have time to write it down. But there is some output. Okay, there's an issue with this output because, which I'll get to in a moment. But let's for now say there's one output, and now what I'd like to do is write a kind of a query processor. We'll call it the local computation algorithm, where I get to make queries to the local computation algorithm. The local computation algorithm we'll call these probes just to distinguish from queries, but it can probe the input at different locations and then output the value of the output at the locations that I'm interested in. So if I'm interested in location I sub 1, I query the LCA, he makes some probes, he outputs y I sub 1. Then I ask about I sub 2, and he tells me, he makes some more probes, and he tells me what's the value of the output y at location I sub 2. Okay, so basically this local computation algorithm, its only goal is for me is to give me a vehicle for accessing the output. And what we're going to do now is write algorithms for these LCAs, these local computation algorithms. Okay, so we're going to see what are the difficulties in coming up with an LCA for the various problems we are interested in. Okay, so we're interested in the running times of these LCAs, the query complexity, how much randomness it needs. So just to make this concrete, and just to point out one of the first difficulties, let's take the problem of maximal independent set. Just a maximal independent set, you're given a sparse, undirected graph, and let me assume for now that for the next several slides, the degree in this graph is bounded by d. So it's a constant degree graph. Think of d as just a constant, so maybe like 100. Okay, so no node has more than 100 links to it. An independent set is a subset of the nodes such that no two nodes are connected by an edge. So the maximum independent set problem is NP hard. This we know, but I'm only asking about the maximal independent set problem. So I'm not asking to solve an NP-hard problem. I'm just asking what's the size of, I want to output a maximal independent set. This is an independent set that may not be the maximum cardinality, but I cannot add any nodes to it to make it bigger, to this specific one to make it bigger. Okay, so there's so this is a maximal independent set. This is something that can be solved in polynomial time by a greedy algorithm. In fact, we'll see the greedy algorithm soon. Okay. All right, so what's the local computation algorithm doing? The input is the graph. Okay, it's given in adjacency matrix form. I'm sorry, adjacency list form, right? So I have just the regular adjacency list format. And now I want to make queries to the output. I want to know, is this node in the maximal independent set? Is this node in the maximal independent set? And that's the kind of queries I'll make. Like, is U in the maximal independent set or not? Okay. So why are we interested in maximal independent set at all? I just want to mention that it's a central problem. It's very important in optimization. It's used for task scheduling. It's used in approximation algorithms. It's central in distributed computing. It's a major building block on which they base many other distributed computing questions. One example would be, can I broadcast without conflicting with my neighbors? And if I have a maximal independent set, then all the nodes in the maximal independent set can safely broadcast. And actually, this is more for fun, but there are, there's some works that think that it's maybe the type of algorithm that fruit flies use in determining which cells are leader cells. So in the brain of the fruit fly, they need some cells to develop as leader cells, but they shouldn't have neighboring leader cells. But also they should have coverage so that all nodes are next to some leader cell. And so this is an example of algorithms in real life. So we think we invented everything, but the fruit flies actually invented it first. So as I mentioned before, maximal independent set is something we can solve in a polynomial time, in fact, linear time, with just a simple greedy algorithm. Okay, and this greedy algorithm is going to suggest to us a perfectly good local computational algorithm. Perfectly good for right now, and then I'll say what I want more. Okay, so what would I do? Somebody asks me, let's say I'm the local computation algorithm. Somebody asks me, is node U in the maximal independent set? Well, initially, nobody's in the maximal independent set, so I'll say, sure. Okay, and U can be in the maximal independent set. Then I'll write down that U is in the maximal independent set, and I'll also write down that all the neighbors of U cannot be in the maximal independent set. Okay, then they start asking me, well, is V in the maximal independent set? So I have to check. Did I write down that V was not allowed to be anymore in the maximal independent set? Because if I did, then the answer is no. But if I didn't rule it out yet, then I can say, sure. As long as none of V's neighbors have been put in the maximal independent set so far, I can say, yeah, put it in. Okay, so that's the greedy algorithm anyways. The greedy algorithm says I run through the nodes in some order, and as long as no neighbors of the node of node U has been put in the maximal independent set until now, then I stick it in. Okay? And then I just keep running through the nodes in that order. So in this case, the order we're running through the nodes is the query order. Whoever made the queries to the local computation algorithm, they determine what this maximal independent set is looking like. Okay? So what's the issue here that's a little bit different from many of the examples, not all of the examples I gave before, but many of the examples I gave before, there was one answer. And here, there are many maximal independent sets in a graph. It all depends on which order you were queried. Okay? So this could be a fine local computation algorithm, but it does have some, in fact, its probe complexity is order D. I only need to check each of my neighbor. Every time they ask me about node U, I just have to check each of U's neighbors and see were they put in the maximal independent set until now. Because if not, I'm safe to put U in the maximal independent set. So the probe complexity is small. But there are some drawbacks to this, and that is I have to remember all my past choices. So I need order n space. Okay, as long as this thing is running, I need order n space. The answer is not oblivious to the query order. As we saw, the answer completely depends on the query order. And finally, let's say I'm running a local computation algorithm over here and you're running one over there, then we're kind of stuck because I'm going to have one maximal independent set in mind and you're going to have another maximal independent set in mind, and they could conflict. Okay, so unless we communicate during the process, we're in trouble. And I have to say, I actually used this algorithm last fall in a real practical setting. I was giving an exam for data structures class for 350 students. And it was just like this. Now we'll demonstrate. So me and the teaching staff, there were like 15 of us in 2 big rooms. And so in each room, there were like 7 of us trying to sit people so that they weren't sitting next to each other. So it had to be a maximal independent set, right? So if you think of the nodes being the seats in the room, and then we had to make sure nobody was sitting next to each other, and we had to kind of compress all these people because there actually weren't really enough seats for all the people in the class. And we had to sort of agree in advance on how we're going to do this. So basically what we did is we agreed in advance on a maximal independent set. The whole course staff, and that's how we sat people. So it's a practical problem, I guess you could say. I mean, it's okay. So what we'd like to think about now is how do we deal with the consistency issues so that we can allow non-interacting copies of the algorithm to be operating in parallel. Okay, so this is our big challenge. And this is the thing that I'd like to emphasize in the model. Here we have a computation problem, F, but there are several legal solutions. Okay, these are all the different maximal independent sets. It could be exponentially many because we're not going to write them all down. We're just going to pick one. Okay, so there's no real bound on the number of legal solutions, but there's a bunch. And what this local computation algorithm needs to do is to implement Oracle access to any one of them, but it just has to be consistent. Okay? So it picks some k and gives you Oracle access to yk. In fact, it doesn't really need to pick the k right away. It could pick it kind of as it's thinking. It doesn't matter, but it needs to pick this k. And for any sequence of queries, this LCA needs to reply according to the same k the whole way through. So if I query I1, then I need to get yk sub I1. Later I query I2 through IQ. I have to use the same k, yk sub I2, yk sub IQ. Okay? So I have to stick to the same legal solution. Okay. And we're going to be keeping track of what is the running time or a number of probes we need per query, and what is the space we need per query. And we'd also like this thing, it's a randomized algorithm, there may be some mistakes. We'd like to have some overall probability of running into an error to be bounded by at most delta of n. Okay, and we'd like the T of n and S of n to be sublinear. So we're hoping to get sublinear time to answer each query as well as sublinear space. Okay, so I guess one other way to look at it is we've got this input. We have this local computation algorithm. We have a random string. We toss it. That picks y sub k for us, so that kind of fixes a solution for us. And then we have to answer always according to y sub k. Okay, so we stay fixed to the same consistent y sub k. That's the main thing of this slide. Okay, so hopefully the whole thing gets tossed by the random string. So what does that mean? That if I have 2 copies of the LCA running around, first, before we go out and work, we share the random string. Okay, and then we can go out and answer queries. But first we need to share the random string. Now we get this random string before we've even seen the input. So the random string is not supposed to be the answer to the I mean, this is a random string we get before we even probe the input even once. And we go off in space, you're working over here, I'm working over there, and we all answer consistently because we all have this random string. That's the goal. Okay, so let's see how we can do this. And I'm going to try to give in the next few slides a whole series of techniques for how we build LCAs. So it's like sort of families of techniques for how we build LCAs, but I'll do it starting with the maximal independent set problem. Okay, so what the goal is, what we're going to try to do is find some maximal independent set algorithm with this nice property that somehow the algorithm itself, if I look at what happens to a specific node V, whether it's in the independent set or not, it doesn't depend on too many other inputs. And that sounds kind of crazy. I mean, what sort of algorithm has like outputs depending on not too many inputs? But actually, in distributed algorithms, they have tons of such algorithms. In fact, and in the recent years, in the last 10, 15 years, they've really made huge strides. It's something, the notion of local algorithms for distributed computation, which is something different. It's a bit confusing that they use the same, that we use the same word that they do. So let me try to, so there's a notion of local algorithms in distributed computation, and there what it means is they count the number of rounds taken by the algorithm, but they have all the processors working at together. In our case, local algorithms are sequential algorithms. Okay, so there's just one processor. In distributed algorithms, they're all working, all n processors are working, and they're talking to each other, but they only take a constant number of rounds. And it's amazing what they can do. Okay, so one thing to notice is if I have a distributed algorithm that requires only k rounds, and we'll see what k can be later, then what Parnas and Ron noticed is that for any v, the output, whether it's in the MIS, in the maximal independent set, or not in the maximal independent set, can only depend on a k-radius ball around it. Okay? Why is that? Let's take k equals 1. Okay? So I have one round of communication. What happens in one round? I send a message to my neighbors send a message to me. Okay, but how did I get the message and how did they decide the message? I read my input, I computed a message, I send it out. They read their inputs, they compute a message, they send it back to me. Okay? That's what can happen in one round, that's it. Like I cannot hear from my neighbors' neighbors, it's just one round. Okay? So I can simulate them because I can read my input and figure out what I would send to them. I can read their inputs. There is just D. Remember we said that D was bounded and it's constant. Okay, so so there's just D neighbors. I can read their inputs, and I can figure out what message they would have sent me. Right? Okay, so for k equals 2, I just have to read my neighbors' neighbors and figure out what they would have sent my neighbors, what they would have sent back, and how they would have computed, and I just simulate this until I figure out what I get. Right? And so as it goes on, so at k steps, I can only receive messages from things k far away. So if I look at all of the inputs in this k-radius ball around V, I can simulate the whole computation that would have reached me. Just the part of the computation that would have reached me in messages. I can simulate all of it. So I can simulate basically the first k rounds that I do, the round k 1 through k minus 1 of my neighbor, that's all I can see from them, and round 1 through k minus 2 of my neighbor's neighbor, and so on. Okay? I can simulate everything in how much time? Well, let's forget about time for a second, but all I need to do is read their inputs, so it's d to the k probes. Okay, so I just need to look at d to the k probes. That's how big the k-radius ball can be. This is why we had to assume radius, that the degree bound was d. Okay, so this is why I'm assuming d. But then I can only grow at most a d to the k in radius k. Okay, how big is k? In other words, for what k do we have distributed algorithms for MIS? Right? Because okay, so this I already said this. Well, the first news that we had on MIS was not so great because it turned out that, for example, the lexicographically first maximal independent set, finding that it's called p-complete, which means it's as hard as possible for parallelizing things in P. So it's one of the problems in a polynomial time that seems to be hardest to parallelize. In other words, if you can parallelize this, you can parallelize everything in P, and we don't think that's possible. We don't know, but you know, people. But it would be a big deal. Let's say if you prove this is doable in parallel time, you can win a Turing Award, I bet. Okay, so so it's a good problem to work on, but I don't recommend doing it for your PhD thesis. Okay, but then that turned out to be a deterministic problem. It turned out if you allow the ability to toss coins, there's a randomized order d log n round algorithm due to Luby. And that in itself doesn't give us a good local computation algorithm, because remember that we take d raised to the number of rounds. So this would be d raised to d log n. So that's not so great because that's superlinear. And we could use the greedy algorithm to do better. Okay, so this is not so good in itself, but we'll see later that it's a very useful tool with additional ideas and different algorithms, some of which I will mention later in the slides, but some of which I'm just going to have to let you read about it, but it's very exciting. You can actually do a lot better. Okay, so I want to say that there's been a lot of work. Almost all of these, Barenboim-Elkin is from 2008, but all these last few are from the last year or two. These. So that was not it when I gave the talk. Something different. Okay. And what's interesting here is the ideas from local computation were used to get better distributed algorithms, and then ideas from that improved the distributed algorithms were later brought back to improve the ideas in local computation. So there has been, so even though it's a different model, a different setting, there has been a lot of interplay between the two areas to help each other out. So currently, the best local algorithm for maximal independence set under certain parameters is due to Ghaffari, who is somebody that works in distributed algorithms, but he was able to kind of blend all sorts of ideas. So let me take the idea of the distributed algorithms that we just saw and refine it one step further. Okay, so I'm going to say sometimes what you want to do is not just take the distributed algorithm and just shove it down and make a local computation algorithm out of it. Sometimes you want to use the distributed algorithm to pre-process your input, okay? And then you can do something else. And in this case, the something else is just going to be brute force, okay? So what do I mean by that? So I want to talk about this Luby's algorithm that we said before was not useful. Okay, because if you just used it with the Parnas-Ron reduction, it had too many rounds. Okay, it needed d log n rounds, so d to the d log n was too big for us. Okay, but let's not use so many rounds. Let's use much fewer rounds, something like d or some order d, and what is going to remain after that is going to be something very useful for us, is what we'll show. Okay, so here's what happens. Let me slightly simplify Luby's. This is Luby's algorithm kind of simplified to its essence, just so I can explain it. Okay, so all nodes initialize themselves to yellow. Oh, this is perfect for this room. Okay. Okay, so everybody initializes to yellow, and now every node marks itself red with probability 1 over twice the degree. Okay, d is the max degree. It doesn't have to be that. Okay, d is the max degree. So every node marks itself red with probability 1 over twice the degree. Now, if I'm yellow, I do nothing. But if I'm red, I do the following. Okay, if all of my neighbors are yellow, I'm marking myself red because I want to be in the independent set. Okay, if all my neighbors are yellow, that means nobody's competing with me. Okay, I'm safe to go. I can put myself in the independent set, and none of my neighbors will do it either, because the yellow guys do nothing, right? So I have no competitor. So I put myself into the independent set, and I delete myself and my neighbors from the graph. Okay, that's what we do. Now I just want to show it, and I'll come back to this slide. Okay, so in this case, okay, wait. What happens if I have a red neighbor? If I have a red neighbor, I do nothing. I go to the next loop, and I start all over again. I mark myself yellow, and they mark themselves yellow. Okay, so here's what happens. If I color myself red, and my neighbors colored themselves red, okay, now each one of those red guys has some neighbor that's also red, so they all uncolor themselves to yellow. Okay? So that's the thing. If nothing happens if I have a neighbor that's red, to me or to him. Okay? So that's nothing happens. But if I'm the only one that's red, all my neighbors are yellow, then I remove myself and my neighbors from the graph. Okay, so now let's see what's the probability that I'm red and none of my neighbors are red. Okay? For me to be red, I colored myself red with probability 1 over 2D. Okay? Now my neighbors are independent of me. So what's the probability none of them are red? Each one of them is red with probability 1 over 2D. So the union, like the probability that any one of them is red, is bounded by sum of 1 over 2D. Like I have D neighbors. Each one flipped a coin with probability 1 over 2D. So what's the probability that of the OR, that any one of them is red? It's at most sum 1 over 2D, and I'm summing this D times. So it's most D over 2D, which is 1/2. Okay? So what I have in here, okay, that's the probability any one of them is red. So the probability that none of them are red is at least 1 minus that. So it's at most 1/2. Okay, so I just made this nice, so it's at most 1/2. So the probability I pick myself to be red is 1 over 2D. The probability that any of my neighbors is, at least 1/2. The probability that none of my neighbors is red is at least 1/2. And so the probability that both I'm red and my neighbors are yellow is at least 1 over 4D. Okay, so I expect to get rid of 1 over 4D fraction of the nodes, at least, at every phase of this algorithm. That's kind of the expectation, right? But then the problem is this, I can expect, but I get rid of 1 over 4D fraction, at some point everything breaks and somebody's going to stay and he's going to kill me, right? Like I expect most people to be gone, but some of them have these low probability events. So there will be some nodes left. Okay, so there will be some nodes left, but what you can show, and this I'm not going to do right now, I'm just going to tell you how we do it. The idea is that after you run order d log d rounds of this algorithm, most guys will be gone, but even more importantly, what's remaining that's still yellow is, I can't bound it. I can't say that there's not that many nodes. There will be some left. And I can't even say that there's not that many nodes. But what I can say is that the remaining components are small. Okay, so there might be quite a few of these nodes, but they will be in small components, size at most logarithmic. Okay, so after we do d log d rounds of Luby, remember before we said for Luby to run completely, you need d log n. But right now we're just using d log d. D is constant, not log n, okay? So we're just using d log d, and we're getting rid of most of the graph, and now most of the components are tiny. Logarithmic size instead of size n that we started with. Those you can just do in brute force. Okay, so this is what happens. Okay. So now what do we do? That was a parallel algorithm that basically pre-processes my graph and leaves it so that it's got these small pieces. How do we build a local computation algorithm out of that? What you want to do is simulate V's local view. So somebody asks me, is V in the maximal independent set? What I want to do is figure out V's local view of this Luby's algorithm. We said we're running d log d rounds. So I can figure out V's view in d to the d log d time using the Parnas-Ron reduction. Remember, it was d to the k, where k is the number of rounds, and we said, okay, you can do that in d log d rounds. So I can figure out if V is going to be in or out in d to the d log d time. It's exponential in the degree. That's why I said it should be constant. And not only that, I can figure out if V's neighbor is in the maximal independent set, if V's neighbor's neighbor is in the maximal. I can look at a little ball around V and figure out who's in the maximal independent set. Each one I'll figure out in d to the d log d time. Okay? In fact, what I'll do is like a little breadth first search. If I see that V is still, okay, so either one of two things happens. I figure out if V is in the maximal independent set. So either I know that it is, or I know that it isn't, or it's still alive. Okay, so I run the view of Luby. For V, I see, oh, I'm dead. Okay, I'm in the maximal independent set, or it may say I'm dead because I'm not in the maximal independent set, but my neighbor was in the maximal independent set. Or it may say that after the ordered d rounds of Luby, I'm still alive. Okay, in the case that I'm still alive, what do? Now I have to figure out phase 2 of the algorithm. Okay, so I'm not in this last case, the third case, I'm not done yet. I have to figure out who is in my live connected component. So I do like a little breadth first search or depth first search to figure out who's in my connected component that's still alive. By always, for each new node that I walk to my neighbor and I ask my neighbor, are you in my component? And he simulates order D rounds of Luby and says, yes, I'm in your component. So then I check all of his neighbors and I check, are you guys in the, each one I simulate D to the D log D time of Luby, and I figure out, are they in the connected component? Eventually, I find this connected component. By the theorem that we proved, okay, by the theorem that we proved, let's call it this theorem here, when we argued that the live connected components are small, I only have to do this logarithmically many times, this breadth first search and calling the Luby thing, okay? So, and then I find my whole connected component with only logarithmic time, and I just take the, say, the lexicographically first maximal independent set on log n nodes. Okay, just something so that if somebody else is going to be computing it from over there, they'll get exactly the same live connected component and the same lexicographically first. We just have to agree on a specific maximal independent set, okay, on how to get it. Okay, so this idea was later used and improved greatly in these works by Barenboim et al. And Ghaffari. And it's often called shattering the graph. And in fact, you could shatter the graph using other algorithms besides Luby. And there have been quite a few improvements. Let me also mention another, okay, so I think at the end I'll talk about what's the best ways to do maximal independent set, but let me mention yet another technique, which is very different than using distributed algorithms, although it's a technique that's also used in distributed algorithms, I have to say. So, and here the idea would be, let's try to simulate this sequential greedy algorithm. The one that I said before wasn't good, and I said it wasn't good because we took the order according to the queries. But let's now say, don't take the order that the query said. We'll take a different order. We'll see which one in a minute. Okay? So again, what greedy does is it runs through the nodes in some order. We'll talk about that in a minute. But what we do is put V in the maximal independent set if none of the neighbors have been put in yet. That's the greedy algorithm. All right. Now this local computation algorithm has to decide what would the greedy algorithm do on U, on node U. So it has to look at you and then look at all the lower numbered, okay, so there was some ordering, right? Where we looked at these nodes, this order here. I have to look at all of U's neighbors that came before you in that ordering and see what happened to them. Were they put in the maximal independent set or not? And then I have to look at their neighbors. In order to compute that, I have to look at their neighbors and figure out from the lower ordered neighbors, which ones were put in the maximal independent set. Okay, if none of the lower ordered neighbors were put in the maximal independent set, then I do go ahead and put myself into the maximal independent set. But if somebody was, then I'm not allowed into the maximal independent set. Okay, so what the problem is, I have to simulate the results of greedy for all the adjacent edges or nodes of a lower ordering. And the dependency chains can be extremely long. So you can easily construct examples where the dependency chain would be really long, just from the line. Just think of the line graph, and there's some order, and even if it's like, let's say node 1, 2, 3, 4, 8, 15, but it's some kind of monotone type order. So I even know that I only have to go to if I'm trying to, now I'm like number 52, okay? I have to figure out if I'm, let's say 152. To figure out if the lowered order, I just have to look right. Okay, and I have to figure out, is he in the graph? And he has to ask, is she in the graph? And she has to ask, I don't know, because I don't know if I'm in even or odd parity from the start, okay, until I go all the way down. So that's a simple example of a long dependency chain. But if you pick a random order, okay, then things are okay. So I said some order. If we fix an order, remember we said the problem was that we don't want the queries to fix the order, and we don't want the graph to fix the order because this line example I just gave you is a bad order. But if the order were picked randomly, most orders are actually pretty good and most dependency chains will be small. Okay, so in fact, Nguyen and Onak showed that most dependency chains would be small, but actually you can show that all dependency, with high probability, all dependency chains will be small. Okay, so that's, you need something further in the, I don't want to really get into it, but you need to use some notions from Galton-Watson branching processes. And so basically this whole idea will work. It breaks down the size to logarithmic of all the dependency chains. And it's going to work for all nodes. Now, one thing that may bother you is how do I keep a random ordering in memory? Like, that sounds terrible. Like, that means the random strings I share, my random string and your random string have to be linear size. Like, because we're talking about a random ordering of all the nodes in the graph. Okay, so it turns out that actually they don't have to be, it doesn't have to be a completely random ordering. It has, so I'm going to say that for those of you that care, I'm going to say if you know about log n wise independent random variables, then that would do the trick here. And then the number of bits you need to share is much, much less than linear. And if you didn't understand what I was talking about, then don't worry about it. Just there are people that know what to do. Okay, okay, okay. So, all right. So what I've described is just one way. There are much better ways of doing maximal independent set based on other. In fact, some of these are based on other distributed algorithms. So basically, this is a collection of people that they came at it from both sides and worked together. And there are all kinds of different maximal independent set algorithms now that you can. The dependence on n that I just gave you was polylog n, but you can get log star n based on a different distributed algorithm. The dependence on the degree that I just explained to you was exponential. If you remember, it was d to the d log d even. But you can actually get so d to the d log d, I think, is something like that. But you can actually make it sort of quasi-polynomial in the degree at this point. So the degree, so it's still a big open question. Can you get polynomial in D dependence for maximal independent set? I think in general, for most of these local algorithms, getting dependence on the degree that's polynomial in the degree is usually an open question. Not always, but usually. So there's, and I guess what I want to emphasize is that most of these works are quite recent. So I think there's a lot of ideas out there that people didn't know that they could use. So I think there's a lot of open questions here that may even be somewhat low-hanging fruit for people that have the right background. Okay, so I just want to mention there is some other problems. I'm going to talk about one other specific problem in a minute, but before I do that, I just want to say that there are local computation algorithms for approximate matching, for other optimization problems, radio network broadcast scheduling, hypergraph coloring. The reason for and KCNF, the reason for these specific three is because Noga alone has a paper on using the Lovász, so if you remember, I said we used Beck's analysis of the Lovász local lemma. So actually, Noga alone gives parallel algorithms depending on that analysis as well. And so these are four of the problems that we could figure out how to solve from Noga's paper. And it was so that's where those came from. But since then, these ideas have been applied to local computation mechanism design, online algorithms. There's actually some more recent work in this area as well. It's been local learning algorithms have been come up with. So there's so it's starting to be applied in many different scenarios. Okay, did I mention? Oh yeah, I did. Okay. All right, and in each of these we get polylog's query and space complexity. I want to also mention that this idea. So the question could be: is this idea that you have random access helpful? Like the idea I said before, let's assume that you have random access into the graph. You can access wherever you want into the graph. Is that a reasonable assumption? Well, it turns out that actually whether or not it's reasonable doesn't really matter, because for most nice graph problems, that ability to make a random access to the graph is actually not that helpful. So you can actually do almost as well without it, basically. So that's not like, So if you remember, even for the maximal independent set, we did random access only to our neighbors, and our neighbors, k times. But we never had to go to a totally arbitrary place in the graph. And it turns out that that, in general, is true for a lot of problems, that you can actually show that for what we call nice problems, and that includes problems like MIS, vertex cover, dominating set, all kinds of coloring problems, spanning forest, matching. Basically, these are problems for which the solution for the graph yields a solution for the maximal connected components. If this is the case, then it doesn't actually help you that you can do arbitrary random accesses. You just need to be able to go to neighbors and neighbors, neighbors. Okay. Okay. All right. So now, if there are no questions, I'd like to move on to a different topic. It's still local computation algorithms, but a different problem. Not maximal independent set, but actually finding sparse connected subgraphs. And this actually is, I won't say as much about this one as I will about the others. This was just posted like 2 months ago. So this is all very like hot, I guess. I mean, I think there's still a lot of open questions here. So, okay, so let's begin at the beginning. We actually have sublinear time algorithms which estimate the size of a minimum spanning tree. Just by sampling the spanning tree, I can estimate the size of the minimum spanning tree under some, okay, I must confess, some pretty serious assumptions, but if you give me those assumptions, I can estimate the size of the minimum spanning tree. The question would be, can I also figure out which edges should be in the minimum spanning tree? It's not necessarily enough for me to know what the weight of the minimum spanning tree is. I may want to know, is this edge in the minimum spanning tree? You know, which edges are actually in it? And those algorithms do not tell you which edges are in the minimum spanning tree. Okay, so they absolutely do not tell you that. And in fact, we're going to see why in a minute. Okay, so let's simplify. Forget the weights. I don't even want weights. I just want a spanning tree. Okay, so just give me a local algorithm that tells me for each edge, is it in the spanning tree? So just like for maximal independent set that we had before, the problem here is consistency, because every edge can be in a spanning tree. I want a consistent spanning tree. Okay, so here's the problem. It's the consistency with the same tree. And here's a reason why it's actually pretty easy to see that getting a local algorithm for even spanning trees, forget about weighted spanning trees, like minimum spanning tree, but even spanning tree is hard, because if I'm this edge right here, how do I know if I'm in the cycle or on the path? Because on the path, I better say yes. I better say yes, I'm in the spanning tree. But one of these guys has to say no. And how can they figure out that they're the one? It's by symmetry, like they should all do the same thing. And how do you, I mean, even with randomness, how would I figure out that one of these guys should say no? Okay, and I can't even figure out that I'm in this case without sort of wandering around linear steps. Okay, so from this, it's pretty easy to see that there is a linear lower bound on just local algorithms for a spanning tree. And that's what, so that's why the answer to this is no. We cannot. Okay? We cannot do that. So we have to simplify the problem somehow. Okay, we already simplified it by taking out the weights, and it was still way too hard. Let's simplify again. Let's just try to sparsify the graph. Forget about trees. I just want a sparse spanning subgraph. Okay, so I want to delete kind of most of the edges, so I'm remaining with a graph that's still connected, and it has 1 plus epsilon n many edges. Okay, so I want it, the main goal here is I'm sparsifying the graph, but I am not disconnecting the graph. Okay, so I'm going to allow a few extra edges. The number of edges I allow is, for a spanning tree, I need n minus 1 edges. I'll give you an extra epsilon times n many edges. Okay, so you can take an extra epsilon times n many edges. Can we do this locally? Okay, so I want now an oracle that tells me provides access to some set of spanning edges, E prime, so that when I look at the graph with just E prime instead of E, it's connected. The size of E prime is at most 1 plus epsilon n. Okay, it's going to be with high probability because there might be too many edges. There's some probability that there might be too many edges. And this new graph should be determined by the original graph and some kind of internal randomness. So it's as we had before. All right, so the question is this new problem easier? And maybe it is. In fact, it is. We're going to see that it is. But there is already an omega root n lower bound. And why? It's hard to distinguish a bridge edge connecting 2 degree n over 2 node random graphs. Okay, so here, these are n over 2 node random graphs. And it's hard to tell if you're this guy, which you should say, yes, I'm in the spanning graph. This guy has to say yes, because it's the only way to get from this side to this side. But it's hard for me to tell if I'm this kind of situation or this kind of situation, where I'm just like an extra edge in an already pretty dense graph. Okay? And the reason is just because of kind of girth arguments. I mean, so the reason actually has to do with some distribution testing problem that requires root n time too, but I'll leave that out. Should I leave that out? Okay. I guess, maybe one thing I'll just say is, let's say you took, say, like a random walk from this guy and started looking at who you see. Okay. Well, even if this was actually, so after taking a few random walks, you're going to see, if this is a random graph, you're going to see random nodes in here. Okay. So let's say I take less than root n random walks. Starting here, I'm going to see so I'm going to see about root n endpoints. Root n times log n endpoints. So, I'm going to take less than root n random walks, each of size log n. So even less, a lot less, like root n over log n, less than that, little over that. So the number of nodes I see is at most is little over root n. And the number of nodes I see from this guy, starting at this endpoint, is also little over root n. And you can show actually that if you look at the endpoints with high probability, there's no intersection, if it's small enough. I'm a little bit cheating. And the same thing here, there's no intersection. So these guys will see, so as far as the view here and the view here, it's going to look identical. And only at root n do I start having collisions. It's birthday paradox type argument. Only at root n do I start seeing the same nodes. So that's why there's a root n lower bound, pretty much. I'm cheating a little bit because when you're really close, you might start seeing each other, but I'm not cheating that much. Okay. Okay, so I just want to mention that some graphs are easier to handle. That was a random graph. It had a very specific property. Some classes of graphs have other specific properties which are extremely nice for us. And it's related to the expansion properties of a graph. So I want to just define, there's tons of definitions of expansion. So I want to define the edge expansion of a set of nodes S. S is a set of nodes. And it's going to be just the number of edges that have 1 foot in S and 1 foot outside of S. Okay, so these are kind of the boundary of S. These have 1 node in S and they leave S. It's that number of edges divided by the size of S. So that's the expansion of S. And the expansion of a graph is the minimum expansion of S. So this is right here a terrible expander because the minimum expansion of this set right here is 1 over n over 2. So it's 2 over n. So this is a tiny expansion. Like random graphs have constant expansion. So I just want to mention this guy's terrible. Random graphs are great. Usually the goal is you want your expansion to be at least a constant. This is going to be tiny, 1 over n. And we're going to talk about non-expanding graphs. So these are graphs we know are terrible expanders, but we want to rule this guy out because this guy is actually, because he's random, he looks good. He's expanding really well until you get to big sets. Okay? I want graphs that no set expands well. All sets are bad expanders. Now, why are these interesting? That includes planar graphs. So it includes a whole important set of graphs. And so these, we'll call those the slow growth rate graphs. These are graphs where all sets do not expand well. Okay, so their expansion is small, and it turns out for those graphs, you just need constant time. You can solve this whole problem of the spanning tree in constant time. And there's a threshold where if your expansion, that's what happens when your expansion is 1 over just a bit more than log t. When your expansion is just a bit less than 1 over log t, then, sorry, your growth rate is slightly faster. I think I said it backwards, what I just said, but whatever's up there is right, I think. Then you need super constant time. There's a lower bound that holds. All right, so there's some kind of threshold activity that says that, okay, we know we need root n for general graphs. There's a class of graphs that are very non-expanding. Those we can do in constant time, and those are kind of the only graphs we can do in constant time, because just when you're a little bit less non-expanding, then boom, we start needing super constant time. Okay, so I'm not going to really explain this. I just want to say that actually, I could have explained it using mostly ideas we've seen in this talk before. But it uses a lot of this. It uses the oracle of the simulating the greedy, the random order thing, to find the non-expanding parts and to do something nice and get a nice partition. And we're not going to talk about that. Okay, I don't know. Okay, so let's just say there's a bunch of algorithms. Some of them actually have other characteristics, I want to say. They may work for weighted spanning graphs if you want something closer to the minimum spanning tree, something like minimum spanning graph, so if you want the weighted case. And there's also a notion of spanners where you not only have your graph connected, but the number of hops you need to get from one node to another doesn't change by much. So if in my original graph, the number of hops I needed to get from U to V was like 10, then in the new graph, maybe I'd only need 12. Like even though I deleted many of the edges, my distances wouldn't go up by that much. So those are called spanners. And they're important in all kinds of applications. So it also gives spanners. Okay, so what I want to do with the remaining time is to give you, okay, I'm going to give you just like an epsilon idea of one of the techniques that gets used, and then tell you about a very recent result of Lenzen and Levy, and which builds on top of it, okay, on many ideas on top of it. It's not simple at all. Okay, so I want to describe kind of a class of algorithms called the centers algorithm, which what we're going to do here is partition the graph into groups where everybody decides to be a center. Okay, so we're going to just pick a bunch of random centers, and depending on which algorithm we're talking about, the number of centers varies. Let's call it C for now. So we're going to pick C random centers, and the way we're going to do this is everybody tosses a coin with probability C over n, and then I expect that C of us choose ourselves to be centers. Okay, so I'm just tossing a coin, okay? And so I'm picking myself independently to be a center. You pick yourself independently to be a center. This coin has very low bias, so very few of us will pick ourselves to be centers. And the expectation is C of us will expect to be centers, okay? And C might be something like n to the 1/3. It's not a constant. It's C for centers, not C for constant. Okay. Okay. So now once everybody picks themselves, okay, so there's going to be some set of centers, and these guys and these centers will now start saying, okay, my partition, the people in my partition are the people closest to me, closer to me than to any other center. Okay? And so we're going to call those the Voronoi cells, just like they do in geometry. And what I'm going to do then is the sparsification of my graph is going to be, I'm going to take a BFS tree, just a spanning tree, which could be BFS. I'm going to use BFS, but I could have used something else, over my component, the guys in my Voronoi cell, and I'm going to exclude all other edges. Okay, so I'm going to have, because these are just spanning trees, there's at most n edges in total, right? I'll show you a picture in a minute. And then between the components, between the different Voronoi cells, I'm going to try to make sure that there's very few extra edges. Okay, I can't have all I can't have all the edges between cells. That I cannot do. Okay, and the difficulty, one of the main difficulties in implementing this thing is a node needs to be able to find its center quickly. So it's good also if the center can figure out who's in its cell quickly, but I also need to be able to find my center quickly, and that can be a problem. Okay, so I'm going to describe a root end time algorithm that works only for expanding graphs, and it's exactly because of this finding the center quickly issue that we run into trouble. So here's how we're going to pick, and this is how we're going to pick the parameters for this particular algorithm. We're going to pick square root epsilon n random centers. And the way we're going to do that is I'm going to pick myself to be a center with probability square root epsilon n divided by n. Yeah, that's right. Divided by n. That's the probability. So square root epsilon over square root n is the probability I toss a coin with that bias. And if that comes up heads, I'm a center. Okay? All right. And okay, this is actually, let me just show you the picture. Okay, so these guys pick themselves to be centers. Okay? Now we're going to do a BFS in a round robin fashion. Okay, so now basically I want to find the nodes that are closest to me, right? So let's say I'm center number 1, and we have we're going to break ties by ID number. Like let's assume we all have distinct IDs, and I'm like first on the list. So I get to pick my, all the neighbors that are 1 away from me first, okay? And number 2 got to pick its neighbors first, second, and number 3 third. Okay, I just want to point out here, now I get the guys that are 2 away from me. Notice this guy was 2 away from me also, but he was already claimed by number 3. So I didn't get this guy, right? Is that clear? All right. Okay, and now there was something else here I wanted, maybe it happens now. Oh, okay, good. I want to point out this guy here, he is the same distance from me as he is from the red guy, but I had a smaller ID number, so I got him. Okay, so for these guys, how do you figure out who's your closest center? For these guys, okay, you could do BFS and find your closest center, right? So first of all, you have to say, when I do BFS, I don't see too many nodes. Okay, and that's the kind of argument that I'm not going to go through in detail is, you need to say, oh, I can do this BFS without seeing too many nodes before I find my center. Okay, so somehow I find the center before I see a lot more than root n nodes is the good idea, is what I would hope. Okay, then the other problem is, what if I find 2? Okay, then of the 2, I need to say I pick the one with the minimum ID. Okay, but it gets a little tricky there because I might see way more nodes before I find all my nodes that are minimum distance apart. And that's the tricky part. Okay, so we'll get back to that in a minute. But we're going to find the partition by performing BFS in a round robin. Okay, so we did that. And now we want to select the edges. So each center takes a BFS tree. And you see, like, we didn't take this edge here. So we already got rid of an edge here. We got rid of all these edges. Okay, we're done with that. And now we're still left with a bunch of edges here that we need to get rid of. So what we're going to do is, for each center, between every pair of centers, we're going to take the edge on the lexicographically first shortest path between those centers. So there might be 2 paths between the 2 centers. Take the one that's first lexicographically. And only take it if it connects the corresponding connected components. Okay, so if this was not the shortest path, maybe there was a shortest path through here, then I don't take this edge. Okay? And you can show that that is good enough, that this will maintain, you can show by an inductive argument that this maintains connectivity. And you can also show that this is, overall the number of edges is n for the BFS tree, and at most root epsilon n squared, which comes from the number of clusters we had, the number of centers. And if we take the number of pairs of centers, that bounds the number of edges you can have between pairs of centers, connecting the different clusters. Okay? All right, so that seems fine. We have not too many edges. But how do you simulate this locally? Okay, so the problem could be that some partitions might be much bigger than others. How do you locally simulate them? So the nice thing about expanders is, so this was an assumption that there is some, these are graphs that grow at a nice rate that's sort of smooth. There's some k where almost all nodes are in a ball of radius k of some center, and no partition is too big. Okay, so in particular, what it means is nodes can find their center in this case. And that's just by finding the closest center and breaking ties via the ID of the center. Okay, so I'm kind of hiding some subtleties in there that you have to make sure this works. But what it gives you for a local algorithm then is, if somebody asks you about the edge uv, is it in the graph? Then what you do is you find the center that claimed u. You find the center that claimed v. Okay, if it's the same center, that means they're in the same cluster. And if they're in the same Voronoi cell. And if they're in the same Voronoi cell, you just figure out, was this edge on the BFS tree or not? Okay? If they're in different Voronoi cells, then you have to figure out if they're on the lexicographically first path that connects their two centers. Okay? Again, this is something that you could do as long as you could find their center. Okay? Because from the center, what you show is that none of the groups are, because, for two reasons. You can find the center, and because we proved that no partition is too big. So this is, we used it sort of in two places. The fact that no partition is too big is only true necessarily when you have an expander, and that's where we use this. And so if no partition is too big, you can just go through the whole PFS tree, and you can figure out what's the shortest path between two centers, because each of them has only like root n nodes in it. Okay? So this is something you can do in root n time. And the query complexity is just the maximum size of one of these Voronoi cells, which is sublinear when you have good expanders. All right, so that's kind of the idea. That in itself would give you an n to the 1/2 plus a little bit more when you have a really good expander. But what about other graphs? And actually, this is still open, but there has been some major progress on this. Recently, it's been shown that you can do all graphs in polynomial in the max degree delta over, forget what epsilon is. Don't worry. Oh, yeah. No, we know what epsilon is. It's max degree delta over epsilon times n to the 2/3. So this is, there's still a gap because we have an n to the 1/2 lower bound and an n to the 2/3 upper bound. So there's still a great set of questions to work on. It happens this also gives a type of a spanner property. But I think there's a whole series of questions here besides this gap to work on, including other types of classes of graphs where you may be able to do better. So I'm going to leave you with that question. So there's also this situation, there's the question of local finding of spanners and the weighted case of minimum spanning trees. And so finally, what I want to leave you with is we talked about a model that distills many of the common features of models that people were already looking at. Some differences would be that this model is intended to handle more general computational problems, such as problems on functions, graphs, strings, and even distributions. The memory access is a little bit more general. It's not clear if it's required in all cases, but we do allow random access in graph problems. It may not be necessary. In distributed, there is a communication graph in the distributed models of local computation. There's a communication graph. You can only talk to your neighbors. Here, we allow you to inspect anybody's inputs. We haven't used it, and we said that on most nice graph properties, you don't need to use it. Okay, and I guess some of the open questions I want to mention is often dependency on the degree is not that good. I've mentioned this a few times throughout the talk. it's often quasi-polynomial or exponential. One of the major areas to look at is whether you can get polynomial dependence on the degree, even linear. I think sublinear might be asking too much. There are some problems. So hypergraph coloring is one of the problems you can solve locally, but not with the best parameters. So there's some questions on whether you can improve some of these parameters for those of you that like that kind of thing. And I think basically any resource management or optimization problem, you may be able to get a reasonable solution locally. It may not be optimal, especially some of these problems are NP hard, but you may be able to get a reasonable approximation in a local manner, and it may have a lot of uses, especially when the data set is so huge and you just want to give people sort of a reasonable protocol to handle locally. And one final area that I think might be interesting is what happens when, in the dynamic setting, when the input is actually changing. How would you handle that? And I don't even know how to correctly phrase the question here, but it seems like that would be a whole set of open questions as well. So I think that's where I am.
Please, any questions? Well, I have some questions. So the first one is you have mentioned matchings, and there is a whole theory of stable matching that is applied to some students and universities or some others. So are there any application of this theory there?
So actually, that's so not, as far as I know, not yet. Not for stable matchings. But that's a very interesting idea to look in that area. So I urge you to go work on it. Stable matchings are does everybody know stable matchings? No. Yes. Okay, so I'll just mention what it is. It's one of the coolest things. Everybody gets a list, and they like. Okay, so this is very old school. There's girls and there's boys, and they can only date girls and boys. So it's and the girl. Okay, maybe we just go to the application. So so there's medical students and there's residency programs. At least this is how it goes in the U.S. And what the medical students do is they rank. I want to go to NYU. I want to go to Detroit Metro Hospital. They rank their residency programs in order. They give a list. The residency programs rank the students in order and give a list. And there's a way of coming up with a matching that is called stable in the sense that I don't prefer to cheat with anybody. There's nobody that so once this matching is determined, if it's stable, then it's the case that there's nobody that could come and ruin our marriage. There's nobody that I prefer that prefers me that could come make an offer to me and ruin my marriage with my hospital. Okay, so in that sense, it's stable, in the sense that it's a very interesting theory. There's actually a whole book written about these and how to find them and whether they're fair or not fair and who they're the most fair for. And so it turns out that the person doing the asking is the person that gets the most optimal solution. So if the men do, in the case when it's men and women, if the men do the asking, then they get the most optimal solution. So it says that women should do the asking. And it has all kinds of interesting societal aspects to it, which I'm not going to go into more, but it's something where I don't think this has been studied at all, as far as I know. So it'd be very interesting.
I have the following question. Can we consider some kind of pre-processing of input data in our model, and how does this model connect, for example, with succinct data structures?
Okay, so I think that if you did consider pre-processing, then it would start to connect with succinct data structures. So I guess it depends on what sorts of preprocessing you allow. So I think the difference between this and many of the data structure questions really is, what do you think of as preprocessing and what do you think of as query answering. So when we talk about number of queries, we were assuming no pre-processing, but it is reasonable to assume some sort of pre-processing, and I think it is an interesting question that I probably should have put there to examine the middle between the succinct data structure. So it's sort of a continuum is the word I'm looking for. The continuum between this model and succinct data structures where you can preprocess in the beginning. And I think it's a very interesting question for future. Yeah.
Thank you for your talk. One question. In most of your asymptotics, you have a dependence on the maximal degree. Is it a principal problem, or we just don't know a better algorithm that doesn't depend on degrees? Because most of graphs in real life have an exponential distribution of degrees.
Okay, so it depends on which problem, and depends on the. So first of all, many times, but not always, one can convert the dependence on the degree to a dependence on the average degree. So sometimes you can get around it that way. Sometimes there's lower bounds for certain problems in terms of the degree, but that's assuming a very tough model where it's adjacency list and that you know nothing about the order of the degrees. So maybe, I'm not sure if it's required. I mean, I'm sure it's required in certain cases if you assume that if it's adjacency list input and that you have arbitrary order on the list of out nodes. In that case, I'm pretty sure that you will need often dependence on the degree. But I'm not sure that there's not some other, like if you assume that that your out node, the nodes you're connected to are always in sorted order, and that you can sort of do binary search. And it's not necessarily a list, but an array. Then maybe you can do better. And in that case, I have no idea. But many times, and not for every problem, it really depends on the problem. You can get a bound that's in terms of average degree.
Have you ever tried to apply this theory to the fuzzy networks?
To what?
Fuzzy networks.
No, I haven't. No.
Is it possible potentially?
So I must confess that I'm not sure I know what a fuzzy network is, but
it's like a graphs but connected with not direct relationship. I mean, you cannot determine the edges as something stable.
I'd see no reason why not, but I guess it depends. So you're saying the edges would actually change?
They're not changing, but you cannot determine it like by numbers. I mean, it can be interval, let's say,
I see.
0.1 to like weighted graph, but with the interval of weights.
Okay, so I don't know. This one I have to take offline, I think, but it's an interesting. If so, it would be very interesting. Thanks.
I have a question about like these algorithms in general. Do they always give correct answer, or do they give the correct answer with a certain probability that is high enough that we care?
Okay, so for example, in the algorithm I showed you for maximal independent set, they would give you the correct answer always, but there is some probability that the running time wouldn't be as good as I claimed. The failure would be in the running time might be too long. So that would be the problem, but it really depends on the algorithm. In the other case, you might get too many edges. So then you get like a bad output with some probability, but the probability is not per query, it's determined in advance. Okay.
You have told that with algorithms we need to have a random access to the elements of an input sets. Is it does a local computation algorithm applied for streams? And can you tell any applications of local algorithm with error corrections code?
Okay, so so for strings, actually, there's a couple of So there's an open question that I like, so I will just say it. Suppose I have two long strings, and we know we can quickly, in sublinear time, we can distinguish the case when the strings have very small edit distance from the case where the strings have very large edit distance. So it's not actually an approximation of the edit distance because it's very weak. It's something we can do, but we can distinguish really small edit distance from really large. So now let's say we're in the case where they have really small edit distance. I'd like a local computation algorithm that gives me the matching, that gives me the matching between the two strings, that shows me that they have small edit distance. So that's a problem that nobody knows how to solve, as far as I know. I don't know how to solve it anyway. And so that would be an interesting open problem. Let's go to another question on strings, which is the compression questions. If you wanted to, so I'll just give an example. There's this Lempel-Ziv 77 compression that gets used in Unix. And if you want to, it's a really good compression for DNA strings because what it does is it finds strings that repeated. And there's a lot of repetitions that happen in DNA. So if you have like huge gene banks, you may want to use Lempel-Ziv 77 to compress them. But if you only want to decompress parts, you can use local algorithms for things like that. So there are some very nice properties for decompression. And for the locally, so you asked also about local local error correction codes. I think that gets used. The first place I know of that it got used was in probabilistically checkable proof systems, which is, I'll tell you what that is in a minute. But okay, so let me tell you what it is. It's a crazy thing. But it's actually being implemented these days. So it's crazy, but it's actually in real systems. In fact, I think it's underlying something called Zcash, which is a competitor of Bitcoin. So it's like real. And one of the things you do there is you need to prove things. So you need to prove things. And a probabilistically checkable proof is a way of writing a proof so that I can write the proof in this special format where you don't need to look at the whole proof in order to figure out whether it's correct. Okay, so this is this cool area of probabilistically checkable proof systems. It was developed, even had seeds in the mid-'80s and all the way through the '90s, and they have these amazing probabilistically checkable proof systems. And I can prove to you all kinds of incredible things, but I write this proof in such an error-correcting format that you can, in just a few queries, determine that my proof is either correctly proving the statement or it's incorrect. You'll have no idea how, but you'll be able to check the format and make sure that everything follows. Okay, it's some way of saying, okay, I take the Turing machine that kind of. So there's some real proof, and I take the Turing machine that looks at this real proof and queries it line by line, and I take this Turing machine computation, and I encode it in such a way that if there was one place that didn't follow from the previous place, it turns into lots of errors. Okay, so it's kind of an error-correcting encoding of a computation. And it happens to be a computation that's checking a proof. And you can do this. It's amazing. It's not simple, but it's amazing. And in that, they need error correcting. They need these types of codes. So you need locally correctable codes because you need to be able to compute these. you need to be able to compute these checks without checking, is this word the error correction of this word? You need to just say, okay, is this bit the right decoded bit from here? And that's the type of thing you need to be able to do. So that's one application. So basically, if Zcash ever takes off, which I don't know it will, because I guess Bitcoin has many competitors, but if that one takes off, then you will be using it on a daily basis. That's my best example. Is it good? Okay. Okay. Yeah.
You mentioned that when simulating greedy algorithm, that you fixed an ordering with a random string, and then instead, because the string would be too long, you instead used a pseudo-random string generated from smaller string, and that generator had to itself be locally computable for you to use it effectively. Are there any other kind of broadly useful building block like algorithms like this one that could be tackled, maybe implemented by someone without extensive background in this?
Oh, I see. Okay, so actually, so there's some very interesting kind of local algorithms for generating random graphs. So this might be something useful. I should say that I've tried to give it's a relatively new area. So as far as like useful techniques, it's all pretty new. So I've tried to give you a sense of what I know so far. There is a bit more, but I think there's a lot of open questions. But there have been some recent works in local generation of random objects. So, for example, there's a work of, actually this wasn't thought of in this context, but fits in this context. It's a work of Goldwasser and Nussbaum, and they show how to generate huge random objects locally. So, for example, if you want to generate a random graph, how would you generate that locally, and how would you also give access to different kinds of queries? So I could just decide, okay, I want to know if you and V are connected. I just flip a coin. That's a random graph. But I may want to also do things like find the next neighbor. So there's some work of Levy, Moti Jung, and some more people, Guy Evan and Adi Rosen, and they show how to generate preferential attachment graphs locally without generating the whole graph from scratch. So it's a very nice paper. It's on arXiv. It's I think it will appear in iCalp next month. So I think there's beginning to be a set of techniques, but I think as a community we're just in the building phases. So we're starting to isolate little blocks, but we're not there yet. But I invite you all to join us.
More questions? Okay, thank you very much once again. It was an exciting talk.
Thank you.